Gauss law. We have already learned to find the electric field intensity due to a charged conductor using Coulomb's law. Gauss theorem can also be used to calculate the electric field intensity provided there is a symmetry in the charge distribution. It can be considered as an alternative to Coulomb's law for expressing the relation between electric charge and electric field. Gauss theorem states that the total electric flux through any closed surface is proportional to the total electric charge inside the surface. Mathematically, it is written as phi equals q by epsilon naught. But we have already obtained the relation that phi equals surface integral of E dot dA. So finally, we can say that surface integral of E dot dA is equal to q by epsilon naught, which is the mathematical form of Gauss law. From this, we get a very important conclusion that the electric flux is independent of the radius of the surface but only depends on the charge enclosed by the surface. Let's take an example. Careful measurements of the electric field at the surface of a black box indicates that the net outward flux through the surface of the box is 8.0 into 10 to the power 3 Newton meter square per coulomb. Then find what is the net charge inside the box. If the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? Why or why not? Solution. Using the relation of Gauss' law, we can write Q equals to epsilon naught into phi. Now by putting the given values, we get the net charge Q equals to 0.07 microcoulomb. If the net outward flux through the surface of the box were 0, then we could not conclude that there were no charges inside the box. Net flux piercing out through a body depends on the net charge contained in the body. If net flux is 0, then it can be inferred that net charge inside the body is 0. The body may have equal amount of positive and negative charges. Proof of Gauss law. Case 1. When Gaussian surface is spherical in shape, consider that a point electric charge Q is situated at the center of a sphere of radius A. Now, according to Coulomb's law, we have the following relation. The electric flux through area element ds is given by, therefore, electric flux through the closed surface of the sphere d phi equals to E dot ds, which is equal to 1 by 4 pi epsilon naught q by a square into ds. Now on integrating d phi over the whole surface, we get the final answer, which proves the Gauss theorem in electrostatics. Case 2. When Gaussian surface is not spherical in shape, then to find the total electric flux, we introduce a new term, d omega which is the solid angle subtended by the area dA at the point, and then we integrate it over the whole surface. On doing so, we get the surface integral of d omega as 4 pi, and then putting it in the equation, we get the total electric flux as q by epsilon naught. Some important points to remember for Gauss law. Gauss law is true for any closed surface, no matter what its shape or size. The term Q on the right side of Gauss law includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. In the situation when the surface S is so chosen that there are some charges inside and some outside, the electric field is due to all the charges, both inside and outside S. The term Q on the right side of Gauss law, however, represents only the total charge inside S. The surface that we choose for the application of Gauss law is called the Gaussian surface. You may choose any Gaussian surface and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charge. This is because electric field due to a system of discrete charges is not well defined at the location of any charge. As you go close to the charge, the field grows without any bound. However, the Gaussian surface can pass through a continuous charge distribution. Gauss law is often useful towards a much easier calculation of the electrostatic field when the system has some symmetry. This is facilitated by the choice of a suitable Gaussian surface. Finally, Gauss law is based on the inverse square dependence on distance contained in the Coulomb's law. Any violation of Gauss law will indicate departure from the inverse square law.